Hello. Hello. So let us continue with what we have last time. Okay. Before going forward, let me emphasize first. Let me correct myself. Um, Correction. When I say mention disjoint, U and your U complement, and if you have V here, this is U complement, orthogonal complement. When I say disjoint here, not necessarily disjoint, but what I mean is they are disjoint on the non-trivial vectors. That is your U and then your U complement. Their intersection is just trivial, like the zero vector. So sometimes I use the term the trivially joint, but almost disjoint. I mentioned disjoint, but anyway, we have already mentioned that before, but anyway, sometimes I forgot. All right. Okay. We will continue with what we have last time. Last time we ended with polar characterization of polar decomposition of a linear operator T, which is decomposed as some isometry, product of an isometry and positive operator, where the positive operator is just a square root of the uh, the product of adjoint of T and itself. And we know this is just an analogy of what we have with the complex numbers and then with our LOV that we have started. Now let's continue with singular value decomposition. I think I want to finish the singular value decomposition so we can proceed with chapter 8 next time. So before this singular value decomposition, so if we have the eigenvalues of our operator, it tells us the behavior of the operator. So another collection of numbers called singular values is also useful, and then we will use this concept. But before that, let's define them. T, a linear operator. The singular values of our T are the eigenvalues of your square root of this, and then with each eigenvalue lambda repeated the dimension of E lambda times. So the singular values of T are all non-negative because they are eigenvalues of the positive operator. So let us give a very explicit example of what's going on. So this is like an easy example because we will deal with easy numbers. So T here, if we have Z1, Z2, Z3, Z4, this is equal to 0, 3, Z1, and then 2, Z2, and then negative 3, Z4. And if you look at the matrix with respect to standard basis, this is just 0 every above, and then 0. Then we have 3, 0, 0, 0. And then we have 0, 2, 0, 0. And then we have 0, 0, 0, -3. Then the matrix of T star is just 0, 3, 0, 0, and then 0, 0, 2, 0, and then 0, 0, 0, 0, and then 0, 0, 0, -3. Thus, your T star, W1, W2, W3, W4 is just 0. This is 3Z2, and then 1. No, let's make it W2, and then 2, W3 is, and then 0, and then -3W4. Okay, thus if we have T star, okay, that's wrong. T star, T of Z. So if we have this as T of Z, then W2 we will get 3 times 3Z1. We have this times this. This here is our W2. This is W3, W4, and then W1. So 3W2 is just 3 times 3Z1, and then 2W3 is just 2 times this is W3, and 0, and then -3 times W4. This is our W4. Again, you can pause that. And then this will give us 9Z1, 4Z2, 0, and then also 9Z4. And then if we get the square root of Z, this will give us 3, 2, 8, 3Z1, 4Z2. Square root of 4 is 2, Z2, and then 0, and 3, Z4. Okay. Now, if you apply this one to the eigenvalues, to the standard basis, then you have the eigenvalues are just 3, 2, and 0. Okay. Now, in dimension of, say, this is our collection of lambdas. For our lambda equal to 3, 3 square root of T star T. This is just the span of V1 and V4. We're in here, V1 and V4 are element standard basis. But here, this is a dimension of this, which is just 2. For the dimension of 2, square root of T star, this is just the dimension of the span of Z of V2. And then the last one, the dimension of 0. And this is just the dimension of span of V3. Which is just, this is dimension 1, this is dimension 1. So that we have the singular values are 3, 3, 2, and 0. So twice, and then this is once, and this is also once. Okay, that's it. Now let's go to the theorem. Each linear operator T has dimension V, singular values. Okay. Them V singular values. This is shown above. We have 4 singular values. And this is seen by applying our spectral theorem to the operator T star T. For example, the operator T defined in 7.50 above, then in this example has dimension on the 4-dimensional vector space has 4 singular values, which is I showed here. So here we will state now our main theorem for this section, which is the singular value decomposition. So the linear operator with S1 up to Sn singular values. Then there exists E1, En. This is orthonormal and F1 to Fn orthonormal basis of V, so distinct, such that T of V is equal to this sum Si VEI Fi. You can think of it as getting the height coordinate of V and then scaling it by the singular value for every V in the vector space. So let's prove this. So using our spectral theorem, you now realize why spectral theorem is important, because it guarantees the existence of orthonormal basis on this. There exists an orthonormal basis E1 En of V such that your T star T applied to EJ is equal to S of J EJ. This is for all our J, for our J that we have defined. Now we have our V can be expressed in terms of its coordinates. So for example, the inner product of V and E1 is the E sub 1 coordinate. And then the inner product of V and En is the E sub n coordinate of V. This is for all V. Then if you apply your T star T to V, you get what do you get? You get this as, okay, let me write this as a sum. Okay, I can write this part as a sum too, but for the sake of easiness, so S sub I, V, T sub I, and then ej. So j na lang. J from 1 to n. All right. This is for all v in the vector space. So using our polar decomposition, we have discussed in the previous video, we have our t here is equal to s square root of t star t. So apply s to both sides. Okay, we will apply s, so we will get e of b is just s square root of t star t of v. It is just equal to s1. Okay, let me write this as a sum. Sum I from 1 to n of s1 in the v coordinate, and then s e1. E I. This is true for each v in the vector space. All right. Now let f sub j be the image of s, the image of e sub j under s. Since s isometry, this will give us our f1 to fn be and also orthonormal basis of v. Then t of v can now be written as this here, jump from here, and then t of v can be written as, okay, we will just rewrite this s I v e I, and then f I from 1 to n. This is also for all v in our vector space v. So this is now our end of proof. And then when we work with linear maps to one vector space to another, we consider a matrix of a linear map with respect to a basis of the first vector space and the basis of the second vector space. When dealing with operators, these linear maps from vector space itself, we will almost use one basis, making it play both roles. So here, what singular value decomposition allows us to use the two different bases of our vector space V for our matrix of the operator T. So how do we do that? So if S1 to Sn is our singular values, then we have E1 to En, and then F1 to Fn. These are distinct orthonormal bases of V. And then suppose that our singular such that your singular value decomposition holds, and here Tij is equal to Sj S sub F sub j. For all j, we have the matrix of our linear map with respect to U1 En, our first basis, and then F1 to Fn, our second order basis. This is just equal to the diagonal composed of the singular values and zero elsewhere. In other words, T linear operator in V, we have M of T is has a diagonal matrix with respect to some orthonormal bases, provided that we are permitted to use two different bases rather than single. Matrix. And we are permitted to use different bases rather than a single customary when working with them. So singular values and singular value decomposition can have applications which will be given in the exercise, including those which are doing computations like computational linear algebra, numerical approximation, and something like that. But again, I will skip that. And then lastly, let me end this by the following theorem. We have a linear operator T on a vector space B. Then the singular values of our T are non-negative. Non-negative square roots of the eigenvalues of your T star T, with each eigenvalue lambda repeated dimension of the E, the eigenspace of lambda with respect to the linear map T star T. This is times. And then, of course, this is the proof here is, again, we will use spectral theorem. And then using spectral theorem, we get orthonormal bases and then non-negative lambda, such that with respect to the orthonormal basis, and then getting that, we can easily see that getting the square root will give us the implied result. So I think we will end here, and then you can check this on the exercise. So that's all. Next meeting, we will start with the last chapter on this series. We will just end the series with operators on complex vector spaces. Maybe I will skip the real vector space, and then maybe we can continue with some topics such as determinants and traces, which are not very, very interesting as our goal here is to develop linear algebra without mentioning the concept of determinants in harmony with what the book is trying to accomplish. So I think I'll end now in this video.